far away. I'll build my webcam.
Kia ora koutou, ko Douglas Walker, toko ingoa. I'm a science teacher at St Patrick's College in Wellington, and my good colleague Andrew Sargent, who's now at Takura, is here with me tonight to help with any of the questions. So I'm going to run through level 1 mechanics, and if you could pop any questions into the chat, that would be great. Andrew will look at those questions. He might answer some himself in the chat, he might pass other ones on to me, or he might wait until the end if there's a sort of general nature to the questions. So we'll get straight into it. Level 1 mechanics. And I should probably say a big thank you to Ministry of Education and Study It for supporting these webinars. Study It's a really useful website. If you want to go on there, you can ask questions relating to your science exams or English and maths, and teachers from across the country will answer those questions. There's a brilliant website that I'm often dependent on, which is No Brain Too Small. And there's heaps of resources for your revision there, some really great stuff. So drop in there and have a look if you haven't already checked it out. Okay, so what we're going to cover today, we're going to look at the assessment reports that are done each year and see what sorts of things stop people from achieving. Once we've done that, we'll go through a common approach to calculation questions. And I reckon if you use the guess approach, there's nothing to stop you getting some credit for any calculation question. I'll go through how to rearrange equations. That's often a sticking point for students leading into the exams. We'll cover speed-time graphs, free body diagrams. We'll talk about work and power, and I'll give you some hints and tips for explanation style answers. We'll cover conservation of energy. That's a common excellence criteria in the level 1 mechanics paper. And we'll look at questions around pressure, force, and area. Okay, so this is quite an exhaustive list, but I think it's really useful. So what people have done, mistakes that have been made in the past that you need to be wary of, not being able to calculate using equations, and we'll probably see some more on that in a moment. You want to be able, with your equations, to identify what each of the letters means and be able to use them in any, calculation situation. You've got to be able to define some of the basic terms, so mass and weight are common ones, as well as pressure. When you're defining those terms, you've got to be able to do it in more detail than just being able to say what it's measured in. And while you're going to put your answers in your own words, stick to the physics. So sometimes responses like, oh, it feels heavier, isn't really going to get you there in terms of the grade. Really common problem here, whether it's at level 1 or beyond, is mixing up energy and forces. So they're two very distinct concepts, and we'll look at those as we go through. You've got to be able to label diagrams with forces and identify common forces like friction, support, reaction, or normal force. You might not be familiar with all of those terms, that normal, reaction, and support are all different names for the same thing. Lift, weight, buoyancy are all common forces that you should be prepared for. So a big mistake that students have made in the past is mixing up acceleration and force. So acceleration is something that happens as a result of an unbalanced force acting on an object. They're not the same thing, so you've got to be really careful not to mix those up in your answers. Looking at a speed-time graph, you've got to be able to make statements about the journey. And any sort of graph that you deal with, whether it's distance time or speed time, you've got to be able to take the information needed from the graph and read the axis labels carefully so that you know on the graph whether it's a speed time graph or a distance time graph, because the way that you work with those two graphs is going to be different. Students may have rearranged formula correctly, but then used incorrect values. So again, the guess method is going to help you with that. don't rely on memory to recall equations. You should have time in the exam to check the equations that you're given and make sure you're not making any mistakes. So always double check. Common mistake is choosing the wrong equation or copying it down incorrectly. So take the time, double check. Got to be able to perform calculations. Make sure you take a calculator into the exam and that you know how to use that calculator. Really interesting one here, not thinking critically about the answers on your calculator screen. So I often see students giving quite an unusual answer for a question, and it's just because of a careless button press on the calculator. So whenever you get an answer on your calculator, think about, does it make sense? And if it doesn't make sense, then go back, check it again. Might be a good idea to double check always anyway. All right, so that's our list of mistakes that are commonly made in the mechanics paper in the past. And now we're going to look at the way that we should be doing things. So common approach to any calculation questions in the mechanics paper is the guess method. So guess is a mnemonic. It's a way of remembering things, and it's an acronym where each letter stands for a different word. So with any calculation, and I'll show you how I'm doing it throughout this webinar, we're going to use G is the given. It's the first letter of guess. And what we do there is we write down the symbol and the value for what we've been given in the question. U is our unknown. So what is the thing that we've been asked to find? And that just comes from reading the question. And so normally I'd write the symbol for the unknown with a question mark as showing that that's what I'm trying to find. Once we've got all the things we've been given and the unknown, we're going to find an equation that fits. And so we'll refer to the formulas that are given, and we should find at least one equation where we've ticked off all of the givens and one unknown, and then that identifies the equation we're going to be using. So that's the list of equations you're given. Get familiar with that. The fourth part of the guess method is substitute. So that's where instead of letters, we put the numbers in. And then the final S is solve. So we perform the calculation, write our final answer. We're going to make sure we do a common sense check so that the number seems to make sense. And we're going to check our units are correct. How to rearrange an equation. So once we've identified an equation through the guess method, here's how we can rearrange it. I'll show you two different ways of doing it. I strongly recommend that you get used to using the first method that I do, but if you're in a pinch and you're really struggling with that method, then the second one is a backup. Yes, Andrew?
No, nothing. Sorry, I just had to mute my mic.
No worries. Okay, so once we've identified the equation, and again, I'll show you examples of this as we go through, we write the equation down. We identify what it is we want to isolate. And so in this case, we might want to find V. I've deliberately picked quite a complex one to rearrange so that you're seeing it done in the hardest possible way that you're likely to see it in the mechanics paper. Once we have identified what we're going to isolate, we're going to get rid of any fractions. That doesn't apply to all of the equations. It's only really the one equation that has a fraction in it. So that isn't going to be a step in a lot of rearrangements, but I want you to be able to do it anyway. And then we're going to do the same thing to both sides of the equation to eventually isolate what it is we're trying to find. By isolate, I mean get the thing that we're trying to find on its own on one side of the equal sign. And whatever operation we do to try and isolate that thing, we're going to do that same operation to both sides of the equation. As long as you do that, you can't go too far wrong. So the first thing we're going to do to get rid of the fraction is to multiply by 2. 2 times a half is 1, and then we don't need to write the half. Remember, we're doing it to both sides of the equation, so then we've got 2ek on one side, and the multiplying by 2 cancels out the half. We're then going to divide through by m to try and get the v squared on its own, and that gives us 2ek over m, which equals mv squared over m. And then we can simplify that a little bit by cancelling out the m's on the right-hand side. And that gives us 2ek over m is equal to v squared. And then there's just one more thing we've got to do to get v on its own. Because v is squared, we need to square root both sides of the equation. And so that's going to look a little bit like this. But because we've square rooted v squared, the square root and the squared cancel out. And that gives us our final equation, which is the square root of 2ek over m is equal to v. When you're doing your square root, be careful to use brackets around everything that's in that equation, so that you've got brackets and then 2ek over m. You might even want to bracket the top and bottom parts of any equation with a division sign in it. So the backup method, if you're really struggling and you're short on time, is the triangle method. It's not great if you're going to go on and study physics any further, but it will get you through level 1 in a pinch. And so for the triangle method, you can draw out a triangle like I've got on the screen there, and then you can pick an equation and fit in the letters into the triangle. So I'm going to use pressure equals force divided by area for this example. And because F is on the top of the fraction, then that means that F is going to be in the top of my triangle. And then the P and the A doesn't actually matter which side they go on, but I'll put P on the left because it's on the left in the equation we looked at, and A on the right. Now, if we then want to work out any of those things, all we need to do is cover it up with our finger. I'll just turn my pointer so it's a bit more visible. So if I then cover up the P, because that's what I'm trying to find, I can see that the F is on top and the A is below the F, so my equation will be force divided by area. If I wanted to work out force, I'll cover over force, and I can see that it's P and A next to each other, so that's times, so pressure times area will give me force. If I cover up the area, then it's force divided by pressure because force is on top. Okay, hope that helps. Give yourself a bit of practice, make sure that you can rearrange equations correctly.
Someone just asked if you could rearrange for m, which I'm guessing the 2k, no, is it 2ek divided by v squared will equal m? Yep. You could probably draw that on there if you wanted to.
Do I want to draw that? I'm trying to think if I've got that coming up on another slide. Yeah, if you wanted to do that, probably the easiest stage to go from is this one here, where we've got 2ek equals mv squared. If I wanted to get m on its own, then I know that I need to get rid of the v squared, and so I would divide both sides by v squared. That would give me 2ek over v squared is equal to mv squared over v squared. Cancel out the v squareds on the right hand side, and that would give me 2ek over v squared equals m. I realize that might have been a bit quick and I didn't write it down for you, but hopefully you'll be able to play back through and just slow down what I'm saying and work that through on your own. Hope that helps.
Someone asked, can you do the triangle method for the kinetic energy equation? Probably not really. Yeah.
You can. It's just a bit. It doesn't get rid of the fraction so easily. So if you were going to do that, you'd have to put because the m and the v squared are next to each other. You could put half m in one bottom corner of the triangle, and you could put your v squared in the other bit, and then ek in the top, and then that would work out all right. But it's going to leave you situations where maybe you want to work out, m, and instead you're working out half m, because you will then cover over half m, and it will be ek over v squared. So you can use the triangle. It's just a little bit harder when you've got more things going on in the equation. All right, so let's put some of that into practice. We've got here the 2020 paper. So we've got good old Felix Baumgartner, and he is jumping off a very, very high object, and then eventually will open his parachute. So we've got his speed time graph. So first thing, straight off the bat, it's a speed time graph. Really important to note that. And we see speed is in meters per second at the side. We've got time measured in seconds, and we've got the line indicating his journey, split into sections A, B, and C. So for question A, we're asked to describe Felix's motion in sections A and C of this graph. Okay, section A, his speed is increasing as over time. So his time's increasing, his speed is increasing as well. So a change in speed over time is accelerating. Now, you can get away with just saying accelerating here, but I've thrown in at a constant rate because I want to highlight something that's a really common mistake in the level 1 mechanics paper. Often people will say accelerating at a constant speed. You can't have a constant speed and be accelerating at the same time. Okay, so you've got to be very careful about the wording that you use to describe acceleration. And so because it is a straight line here in section A, that means that it's a constant rate. You're not going to have to deal with anything more complex than that in level 1 mechanics. So any acceleration is likely to be at a constant rate, not a constant speed. Hope you understand there that you can't have a constant speed and be accelerating. All right, section C. Well, it's a flat line, which means that the speed is 350 meters per second the whole way along section C. And so we can say constant speed and we can get away with that, but I would always throw in that little bit extra detail of the value of the speed. In this case, we're asked for the speed as part B. And so we know that the highest speed on the graph is 350 meters per second. So we get achieved for part A, and 350 meters per second for part B is another achieved. Okay, in part C, we've got to use the graph to calculate Felix's acceleration in the first 30 seconds. So I've used little construction lines here just to mark off that part that we're interested in. And we can see there that that gives us a change in velocity. If you haven't used this little triangle symbol before, that's delta. And you'll have noticed that it's on the equations that you're given in the exam. So that just means a change in velocity. So the delta means change in. And so what values have we been given? Well, we've got a change in velocity. It's gone from 0 to 300. So change in velocity is 300 meters per second. We're also given time. It goes from 0 to 30. And so that's 30 seconds. Delta t is change in time. What's our unknown? Using the guess method, I've written A for acceleration equals question mark. And I know that we're looking for acceleration because I've read it in the question. Okay, the E of the guess method is equation. And so we're looking for an equation that has these things. And we should be able to identify quite quickly and easily that it's A equals delta V over delta T. If you're struggling a little bit with that or you need a bit more time with it, just go through and tick off on the equations every instant of delta V and every instance of delta T and every instance of A. And you'll find that there'll be one equation that's got all three of those things in a way that you can use it. So identify which equation I'm going to use, and then I'm going to carefully write it down in my question so I haven't made any mistakes as I copy that across. And then I'm going to substitute. So 300 divided by 30. And before I do this on my calculator, I'm going to run through a common sense check. Okay, 300 divided by 30. I've probably got a reasonable idea that that's going to come out at around about 10. And so any number other than 10 would suggest I've made a mistake in my calculator. The other really good common sense check here is that Felix is on or above Earth, and so we would expect the acceleration to be about 10 meters per second squared. Sure enough, 300 divided by 30 is 10 meters per second squared, and so that's his acceleration in the first 30 seconds. Make sure I check my units. It's meters per second squared. Common mistake is mixing up meters per second, which was what speed is measured in, with meters per second squared, which is acceleration. Okay, and while that seems like quite a lot, it should be a fairly easy calculation, and it was achieved. Okay, distance traveled. So with a speed time graph, we should know that distance traveled is the area under the graph. We're asked to calculate how far he fell in the first 30 seconds. So we're still dealing with that triangle part of the graph. Distance traveled is the area under, and so I'll shade that in. And because it's a triangle, we know that the area of a triangle is half times the base times the height. Our base is 30 and our height is 300. So that gives us half times 30 times 300. And that should come out, again, doing it carefully on our calculator. 3 times 300 is 900. times 10 is 9,000, half of 9,000, 4,500. So we know that it's going to be about 4,500. That gives us excellence if we get that one right. On to question 1, part E, forces. It was quite a long question 1 in this paper. So we've got to draw and label arrows on the diagrams below to show the size and direction of the vertical forces acting on Felix in sections A and C of the graph. So we've got section A and C, a little Felix for each of those situations. There's really important to highlight that label on the arrows. A lot of responses examiners will see will be missing labels from the arrows. The other thing that I really want you to do is take a ruler into the exam with you and to carefully draw your arrows using a straight line and measure them. Make sure that if the arrow should be the same size, then you've measured it out. Okay, so label, and we're going to show the size and direction of the vertical forces on Felix. So there's our first arrow. We should know that downwards, we've got weight force. You'll get away with calling it gravity, but probably the better terms to use is force due to gravity or weight. And so I'm going to use weight, and I've labeled it up there. Note that I've started my force arrow from the center of the object and then going in the direction that it's applied. So the weight is downwards, and then we're going to have an upwards force here because he is falling and he's bumping into air particles, but we know that he is accelerating in section A. Now, he can only accelerate if the net force is downwards. So the net or overall or resultant force is downwards. And so that means that the upwards arrow must be smaller than the weight arrow. Otherwise, if the upwards acting arrow was the same size as the weight arrow, he couldn't be accelerating. And so I'm going to call that upwards arrow. You could get away with calling it friction, air resistance, drag. All of those are acceptable terms here. Make sure it's clearly labeled, make sure it's drawn with a ruler, and make sure that if you measure 3 centimeters for weight in this case, then your friction arrow, you're going to want 1 or 2 centimeters. So it's clear for the examiner. In section C, we've got constant speed, so he's no longer accelerating, and that can only happen if the forces are balanced. So by that point, he's now moving fast enough to be bumping into enough air molecules every second to provide an upwards force that is equal to his weight force. Really important point here, Felix hasn't stopped for a KFC on the way down, and so his weight is going to be the same because his mass is the same. And he's still in Earth's gravitational field, so his weight cannot have changed. And so there were some cases in this paper where people, drew the weight downwards in both situations, but the weight changed, and that shouldn't happen. It's possible that you get marked down for that. But in section C, as I mentioned, the friction force must now be equal to the size of the weight force, but acting in the opposite direction. And that's excellence if you get all of that right. Okay, so now we've got to explain that, and I've kind of done that already, but we'll do it in writing, and I'll talk through it again. So in section A, downwards weight force is larger than the upwards force of friction caused by air resistance, so there is a net or overall or unbalanced force downwards. That's going to result in a downwards acceleration, and I've put in N2 in brackets there, that's N2 in Roman numerals, as referring to Newton's second law. So an object acted upon by an unbalanced force will accelerate in the direction of the unbalanced force. And that's what we're seeing in the diagram for section A. In section C, the downwards weight force is equal to the upwards force of friction, again from air resistance. So there is no net or overall or unbalanced force. You don't need to say all of those terms. I've just thrown them in there because you might have been taught different terms, and I didn't want to confuse you. An object acted on by balanced forces will not accelerate. It will only maintain its speed and direction. That's Newton's first law of motion, hence N1 in brackets. It's a shorthand way of saying Newton's first law, and that's going to result in a constant speed downwards. I know that I might be moving through that rather quickly, but the beauty of this being recorded is that you can play it back and spend more time on this one if you need to.
Just answer someone else's question. Does it matter how big your arrows are for balanced forces as long as they're the same? Nah, not really.
Yeah, Andrew's exactly right there. Just make sure that they're the same size. The other little trick you can do with that, and you might have learned it in maths, is that you can put, on this case, if I drew a little double horizontal line on each of those arrows, so on the downwards arrow and on the upwards arrow, even if I've drawn them different sizes, that indicates that you mean them to be the same size. But don't let it get that far. Bring your ruler, measure the arrows, do it carefully.
Someone asks, what are all of Newton's laws? I'll just quickly fire through them. The first law is the law of inertia. So it just means something will keep on moving with a constant velocity, or just for level 1, constant speed, unless a force X on it.
Unless an unbalanced force acts on it.
Yeah, unbalanced force X on it. So an example of this is if you're in the middle of space and you throw some rock, it'll just go forever unless it gets into some gravitational field. The second law is literally just force equals mass times acceleration. It's just the formula. And the third law is the equal and opposite forces law. I'm not quite sure how much detail you go into in level 1. But if you push on something, it experiences the same force that you act on it. So I know you push on a table, the table pushes back up on you. If you stand on the floor experiences the exact same force that you push down on it. It's just the opposite direction. Hopefully that makes sense.
Yeah, I don't think you'll need Newton's third too much in level 1 mechanics, but yeah, thank you for running through those, Andrew.
Cool. And someone mentioned whether you needed to mention them. No, you just need to know what they are. You don't need to know like what numbers they are. Just know that they exist.
Okay, so question 2, energy and power. We've got firefighters running up the Sky Tower. So we've got Lindley doing a bit of a jog up the stairs in her building. She climbs to a height of 25 meters, and we're showing the data for 2 different journeys that she has taken on different days. So in both cases, Lindley and her equipment has a combined mass of 80 kilograms. The height that she's climbing or running up is 25 meters, and it takes her 50 seconds on day 1 to do that, and 30 seconds on day 2. We're asked to compare the work and power produced by Lindley on each of these days. And in our answer, we should calculate the work done on each day and calculate the power used on each day. And a little bit of a tip here, you really want to be highlighting words like compare, discuss, explain, because I probably would have approached this just looking at the bullet points. I would have ticked off each of those bullet points and gone, yep, sweet, I'm done. But because it says compare, you're expected to then write a little bit about how those might be the same or different. So let's see how we go through that. I've just, to make a bit more space, move things around here. Again, using the guess method, we've got mass, we've got height, and we've got 2 different times. So I've used T1 and T2 to indicate the times on the different days. Our unknown is work done. We're being asked to find work done. Really important thing here is to understand that work done is energy. So we could use E or W for the work done. And we're also asked about power. We'll come to that. So for our guess method, for the first step, we've got given, unknown, next letter is E, we need an equation. All right, we've got a whole load of terms here. We can use W or E in order to find our unknown. And so in going through the equations that we've been given, we might find EP equals mgh. But there's a little bit of a problem here because, hang on, what's G? Well, conveniently, G is given to us not far away, and that's the gravitational field strength or acceleration due to gravity. So you might have seen that written as G equals 10 meters per second squared. It's given here as newtons per kilogram. They're the same thing. So we're going to use this. It's going to be important to include in our equation. And so I would use the equation that the change in EP, change in potential energy, is equal to mass times gravitational field strength times height. Substitute in the numbers, we've got 80 times 10 times 25. And so, you've got a bit of an idea, hopefully there, that what sort of ballpark your answer to be in, should be in. 10 times 80, we're going to be looking at 800. Another 2 lots of that, so that's then times 10 twice more, 8,000, 16,000, plus another 5, which is a half of that. So we're probably looking at the, in the region of the high tens of thousands for an answer. And if you're reasonably good at maths, you probably worked out that that was 20,000. So 20,000 joules. Don't rely on mental arithmetic though. Double check everything you do with a calculator. So what I've done here is I've just changed my unknown now to 20,000 joules because in calculating the work done, we've still got to work out power. But in order to get the power, we need to know the energy or work done, because we can then use that as one of our values to find an equation suitable for use. And we'll probably stumble across power equals work done divided by time. I tend to write that as P equals E over T because I'm used to referring to energy as E. So that's going to be the second part of our calculation here. So I've now written P equals question mark. And on day one, because it's each day, I'll just go back and say that because mass times gravitational field strength times height was the same on both days, then we don't need to do a second calculation for that for day two. Okay, but for power, we can see that the time is going to be different for each day. And so we're going to need two different calculations for power. So day one, we've got power equals work done divided by time. I've used the little subscript 1 to indicate day one. And that's 20,000 joules divided by the time of 50 seconds. And that gives us 400 watts. If you're not sure, if you can't remember the units are watts, then you can actually just use whatever the units for energy were divided by the units for time. So we know that energy is measured in joules. We know that time is measured in seconds. So it's entirely acceptable to put your units for power as joules per second. On day two, again, we've got the power equals work done divided by time, 20,000, but this time it's divided by 30 seconds. And that gives us 667 watts. That's merit. And then
someone just asked a quick question. I'll go through it now actually. So someone said, can you substitute E for work? So work is force times distance. Potential energy is literally just mass times gravity is a force and the height is the distance. So the energy that you gain is work done. Because it's mass times gravity, which is force, because gravity is acceleration. So it's, mass times an acceleration times a distance, which gives you an energy. Someone said, is work energy? Yes, but it's the exchange of energy. So it's from one to another. In this case, it's gravitational potential energy, probably just getting exchanged to velocity. They're what will be the exchange that's happening. And you don't need to memorize the units. The units, you can either write them as joules, so you've got potential energy as joules, or you could write it as all the units that are in the equation. So you've got mass, the acceleration, and then height. So you could write kg, meters per second, meters, because they are all the units that are in the equation. However, if you try and remember that energy, the units are joules, and you should probably know that because on the packs of food packets, it's all measured in kilojoules or joules.
Yeah, I wouldn't. While Andrew's absolutely correct, I wouldn't recommend writing out the units by such a long way. I think you'll give an examiner a heart attack if you do that. But yeah, he's absolutely right. As I mentioned at the start, work done for level 1 purposes, you can consider work done as energy, and so you can use them interchangeably.
Last question was, thought work was a force applied over a distance, which is totally true. So gravitational energy exchange, you've got mass times gravity, which is force, and the distance is the height.
I think I might have covered that in more detail in one of the earlier videos. And so if you have a little look back through at level 1 mechanics, ones that I've done in previous years, I think there's an example that looks at that, the similarities between work done equals force times distance and EP equals mgh with the ramp situation, just so that they're effectively the same thing in terms of the equations. So there we've got as the change in potential energy is mgh, and since G, height, and Leslie's mass all remain constant, the work done will be the same on both days. And then since power equals work done divided by time, a smaller time on day 2 with the same work done will result in a larger value for power. It's really important in anything where you're comparing or explaining that you state what stays the same. So classic thing that people miss out on is you say what changes, but you don't say what stays the same. So make sure you explicitly state each thing that stays constant in a situation. And then that would bring you to excellence. Okay, so a bit more energy and power here. This is a classic excellence question where we've got an object that's falling and we're given its velocity, or we need to work out its velocity. And so this is using something called the conservation of energy that you should be familiar with. The mass of the helmet's 1.5 kilograms, and we're going to find the height at which it fell from. So we need to calculate the kinetic energy of the helmet just before it hits the ground, and then we need to describe from which form this kinetic energy has transformed. Once we've done that, we'll be able to work out the height from which it fell. So standard achieved level point here for anything relating to conservation of energy is a simple statement like change in EK, kinetic energy, equals change in EP. So what have we been given? 20 meters per second, 1.5 kilograms. What are we being asked to find? The height. But we've been asked to calculate the kinetic energy. And so actually our first unknown is kinetic energy. That allows us to work out EK because we've got M and V already. Really important to remember this squared bit. Okay, it's often the case that people miss out the squared in their calculation. So if you're using EK equals half mv squared, make sure you're doing the squared. Go back and double check it. That's going to come out at 300 joules for the kinetic energy. So because kinetic energy, the change in kinetic energy is equal to the change in potential energy, so whatever potential energy was lost as the object fell has been turned into kinetic energy. And so we can take the value for kinetic energy and we can drop it into the EP formula. So that should have had a little delta EP there, but never mind. So we can rearrange that to, if we want H on its own, we can divide both sides by mg, and that gives us EP over mg. Because the mg is on the bottom of the division sign, I've put brackets around it. Otherwise, your calculator is going to throw out a wrong answer for you. Well, what the calculator is doing is correct, but because you didn't put your brackets in there, it's doing it in the wrong order. Okay, so I've just put a little note on there about that. You can try it out on your calculator. It's a good way of reinforcing that. Okay, so that gives us H equals 300 divided by 1.5 times 10, so 300 divided by 15. And that comes out at 20 meters. So we know that the object's fallen through 20 meters. That gives us an excellence answer. All right, I've thrown this in here because there's a bit of a, the other one you might have to rearrange is the EK equation. And if we do that ahead of time, it actually gives us a bit of a shortcut. So in this situation, we've got a skateboarder starting at the top of a high ramp, and he reaches a speed of 12.7 meters per second. That's his top speed, which must happen at the bottom of the ramp. So we refer to the law of conservation of energy. Change in AP is equal to the change in EK. And we know the formulas for those two. So we can do a little bit of algebra here to whittle that down to a shortcut. Because we've got the half, and I hate having fractions, we're going to multiply by 2 to give us 2 mgh is equal to mv squared. We can then divide through by m, and we've got it on both sides, so that's going to make things look a little bit tidier for us. And it comes down to, when we cancel out the m here and here, it gives us 2gh is equal to v squared. Okay. Now, if we want to get the height, we can divide both sides by 2g, and that gives us this formula here. We know that on Earth, g is 10 meters per second squared, or newtons per kilogram. And so that gives us a formula of h equals v squared divided by 20. Okay, h equals v squared divided by 20. We can then substitute in our 12.7, making sure we're very careful with that squared. And then we've got the answer, which comes out at 8.06 meters. And the reason I've shown you that is because even if you're not too sure about the way that we got there, you can take this equation and use it as a shortcut in the exam. So you've got height is equal to v squared divided by 20 for any object falling on Earth, ignoring air resistance. And I'm going to put in a wee note at the bottom, because the other way we could have done that is we could have isolated v. So we could have tried to get v on its own, and that would give us v equals square root brackets 20 times height. And that's a little shortcut that often gets us very quickly to an excellence level answer in mechanics. Okay, so back over to our 2020 paper. Explain why the helmet will not reach a speed of 20 meters per second. And that comes into what I mentioned a moment ago about air resistance. So from consideration of energy, I quite like this one actually, because there's two different ways of considering it, even though the schedule really only focuses on one. So probably the one that's being emphasized by the question maybe a little bit more is energy. And so we'll start off with that one. In reality, not all of the gravitational potential energy will be converted to kinetic energy. Some of it, because the helmet's falling down, it's bumping into air molecules, it's going to make those air molecules move a bit, and we're going to call that friction, and we'll say that some of that energy will be lost as heat through friction. So as the helmet's colliding with air particles. Since EK equals half mv squared, and this is a little trick for you, in your explanation answers, use an equation to support your answer. So what I do is I write since and then the equation, and then I'm going to make sure that I talk about every term in the equation. So if mass remains constant, tick off m, but EK decreases, tick off EK, then velocity will also decrease, and I can tick off a v. So I've then talked about everything that's in the equation, and that means that you're more likely to do everything that's needed of you to get excellence. Okay, we could also consider it from forces. And so the previous calculation, because the question didn't say only using energy, I think it would be perfectly acceptable to use forces. It's probably not as natural for most people at level 1, but the previous calculation assumes that weight is the only force acting on the helmet as it falls. Now that's true at the start of the journey, so as soon as you let it go, but as it is moving through the air, then it's bumping into air particles. So in reality, the helmet's going to be colliding with air particles, causing friction, and that's going to reduce the net force acting downwards. Because F equals ma, remember that little trick to put the equation in your answer, this reduced net force will result in a smaller acceleration as mass does not change. So if you keep mass the same, and you're going to decrease the force, the unbalanced force, then that has to decrease A as well. And so a smaller acceleration will mean the helmet reaches a lower velocity than predicted. All right, excellence. Okay, question 3, mass, weight, and pressure. You want to be going into the exam prepared to discuss mass and weight. So have some definitions, rote learned, ready to go. Define mass and weight. Mass is a measure of the amount of matter in an object and is measured in kilograms. Weight is the force exerted on a mass due to a gravitational field, and weight is measured in newtons. So it might even be that you want to just use the wording that's there and take that into an exam ready to use it. That's achieved level response, but it comes up often enough to warrant being ready for. Explain what 10 newtons per kilogram means. Well, that means 10 newtons per kilogram, just taking the newtons. Kg to the -1 means per. We could write it as N divided by kg if we wanted to instead. So newtons per kilogram. That means that there's 10 newtons of weight force acting on every 1 kilogram of mass. So if an object on Earth has a mass of 2 kilograms, it's going to have a weight of 20 newtons. And it's quite good to give a little example there so that you're really showing that you understand what you're talking about. That's a merit level response. And then you can expect something along this in the paper somewhere. So we've got to calculate the weight force of the Mars vehicle when it's on Earth and when it's on Mars. So being able to use this equation to work out weight of an object. So the mass of the Mars vehicle is 2,500 kilograms. Part 1, weight of the vehicle on Earth, where G equals 10 newtons per kilogram. mass, and this is just going through the guess method, mass 2,500 kilograms. G is 10, which is also acceleration due to gravity. And now I've put W or F here because it's, you might say, well, I'm working out the weight. The weight is force. So weight is a force. And so you may have learned W equals mg, weight equals mass times gravitational field strength, or you could look at that as F equals ma, it's mass times acceleration due to gravity. Okay, and that's going to give you your weight force. So I've put a little FW here, subscript W, to mean that it's weight force, not anything else. 2,500 times 10 is 25,000 newtons. Weight of the vehicle on Mars. So the only thing changing here is G. Oops, should have changed. I haven't changed that on my slide, so that says 3.7. I'll fix that up afterwards. And that gives us 2,500 times 3.7, which is 9,250 newtons. And that's an achieved level response. I think the way it's marked, if you get either of those correct, you get the achieved, but obviously you want to get everything right. Okay, last little bit, pressure. Again, you could go into an exam with a very high chance of having to deal with a pressure question. Classic trick is that it's going to give you multiple points of contact on the object. So like a chair might have 4 legs, and so you might get the area for one of the legs of the chair and know that you have to multiply by 4. In this case, we've got 6 wheels of the vehicle, and we're told with a surface area of 0.25 meters squared per wheel. That means that the total surface area is going to be 6 times 0.25 or 1.5 meters squared. Calculate total pressure. So given area is 0.25 meters squared, and so we get total area. We've got the weight force from previous, and our unknown is pressure. So it shouldn't take us long to find the relevant equation from our list. We've got P, we've got F for force, and we've got capital A for area. It's going to be this one. Write that down carefully, making sure that you transcribe it correctly. Substitute, so drop the numbers in, and then solve. And so we should get an answer on our calculator. It's going to be a recurring number, so it's going to have a decimal place and keep going. Significant figures aren't too much of a worry, but I would give it to 2 or 3 significant figures. In this case, I've written it as 5. It doesn't make any difference in terms of the marking. Pressure is measured in pascals. If you weren't sure about that, then force is measured in newtons. Area, as you were told, is meters squared. So you could give your answer as newtons per meter squared. And that's excellent. Part E, Mars vehicle is placed on similar soils on Earth and on Mars. Explain why the Mars vehicle will sink to different depths on each planet. You should support your answer with a calculation. Okay, so once again, pressure, force, and area. And so this time we've already got it for the previous situation, which was Earth, where it was 16,667 pascals. On Mars, the pressure works out to be 6,167 pascals, so considerably less. I've written down the value for Earth there just to help us compare it. And again, using an equation to support my answer, since pressure equals force divided by area, and area remains the same, take off area, on Earth and Mars, it is only the weight force of the vehicle that changes. On Mars, the weight force is smaller. It's really important to say on which planet is smaller to show that you understand what's going on here. And if the weight force is smaller, the pressure must also be smaller. This smaller pressure means that the rover will not sink as deeply into the soil on Mars as it would on Earth, or vice versa. And that is an excellence level response. Okay, so what we've covered, we've looked at learning from past mistakes. We've looked at the guess approach to calculations. Use that approach, and I fully believe you can't go wrong in terms of picking up credit. Never leave a calculation question blank. Always use the guess method. Rearranging equations we've covered. Go back and have a look at that if it's something you struggle with. We've gone through speed time graphs, and what we haven't done so much is go over distance time graphs. The important distinction to be made there is that on a distance time graph, the gradient of the graph gives you your speed or velocity. So if you've got a diagonal line on a distance time graph, you can work out the gradient of that line using rise divided by run, and that will give you the speed of the object for that section. We've gone over free body diagrams and the important things you need to note for them. We've talked about the link between work and power using both theory and calculation, so explanation and calculation. We've gone over some techniques for explanation answers as we've been going through. We've had a good look at conservation of energy and a couple of different examples of questions you might be asked where you have to relate potential energy to kinetic energy. And I've shown you a couple of shortcuts on those. And finally, we've looked at explanations relating to pressure and, of course, those definitions for mass and weight. All right, how are we doing for questions, Andrew?
So there was a question quite a while ago, but I said we'll save it to the end, about substituting equations into equations. Doesn't really come up that much in level 1, to be fair. I can't really think of any. Have you got the formula sheet on hand?
Yep.
Because the other question, there was 2 questions that we missed. Was could you go over all the units you need to know for mechanics and what you use them with?
Good call.
Straight off the bat, I'll just put out there. Normally, you actually can get away with not even having units in the questions. It's not good practice, but from marking NCEA before, if you forget to put the units in the answer, unless the question specifically asks for it, often they just let it slide. But yeah, you shouldn't really do that.
I think for the units, we've probably actually talked about everything that's in there throughout the course of this webinar. Velocity is speed, meters per second squared. Nearly said squared there. Meters per second. Sorry. Distance, meters. Time, seconds. Acceleration, meters per second squared. So that's the ms to the -2. Force is newtons. I quite like how that's got F net. I sometimes call it unbalanced force. I'll put a little U in front of it. Mass is kilograms. Acceleration, again, meters per second squared. Pressure is pascals or newtons per meter squared. Force newtons. Area is meters squared. Energy, any form of energy, is joules. G, you're given as newtons per kilogram or meters per second squared. It's just the same as acceleration. Height, normally meters. EK is joules. Mass, kilograms. Velocity, we've done. Work done is energy, so it's joules, or transfer of energy, as Andrew correctly pointed out. Force is newtons. Distance is meters. Power is watts, but you can give that as joules per second because that is energy and that is time. And that's all of the units. What was the other question, Andrew, about putting an equation into another equation?
Yeah,
you could.
Really,
I guess, you could do it in a level 1 paper. I normally wouldn't do that until, I just naturally don't do it. I tend to do it as 2 separate steps, but each to their own. So I'm probably not going to cover it here. But if you had, for example, the change in velocity and a change in time, and you ultimately were trying to get to the unbalanced force that was acting on something to make it accelerate, you could take F equals ma and you could put in for A delta V over delta T. So you'd end up with F net equals mass times delta V over delta T. Right. Good question.
Yeah, that pretty much covers it.
Okay, no other questions? I'll give it a moment.
No, that looks pretty much about it. I think we've covered everything else. So I want to set up there. Could we not substitute the values with numbers and do it another way? You can just do numbers instead of the symbols that relate to it. I think for level 1, for most students, they feel most comfortable putting the numbers in first. But what you should do is you should write the equation first, then put the numbers in afterwards.
You're still going to have to rearrange either way, whether you put the numbers in first or not. But yeah, look, totally, you can do that. And I think actually in my notes, I didn't say it, is that sometimes it's easier to put in the numbers and work out mini steps of the calculation. So an example would be, if we went back up to
probably that half mv squared equation.
Yeah,
could,
if we
solve about halfway through.
Yeah. So if you were doing this one and you got to this stage, You know, you might put in, if this was what you were doing, you might put in the M and the G first and then multiply them so that you just get a number next to H, and then you might find it easier to rearrange. Yeah, that's absolutely fine. So we know, for example, we know that G is 10, we know that mass was 1.5, 1.5 times 10 is 15, and so we could say that EP equals 15H, and that might then be easier for you to deal with.
That looks to be about it. I think that's all the questions.
All right. I think we can probably finish by saying that the biggest recommendation I would have for any students working on their exam questions, exam revision, is to use practice papers. So go back through, you know, if you've done the last 5 years of practice papers and you've carefully tried to do it yourself first and then checked your answer against the schedule to make sure that, you know, if you've missed anything, you then add it in. You're not going to hit any surprises in the exam paper. So the questions are very similar year on year, which makes it really easy for you to prepare. You just got to make the time and go through those old exam papers. You can get those on NZQA. You can do a search for NCEA L1 Science Mechanics, and you'll probably find the NZQA site. The other really good place for that is No Brain Too Small. And so No Brain Too Small take the exam questions and then separate them by type. So if you've got, if you want to do lots of those conservation of energy kind of questions, you can go onto No Brain Too Small and you'll find lots and lots of them all collated on one PDF. And the answers are also on No Brain Too Small, collated in the same way. Okay. Anything to finish with, Andrew?
Just chucked in the chat the last 3 years of exams, like the walkthroughs, and I'll chuck in your here it is, your level 1 science videos as well.
Awesome, thank you. Yeah, I've got a few more videos on the genetics, mechanics, and acids and bases from previous years. So if this was helpful, then you can go and check those out too.
Yeah, so if you want to open them up, you have to open up the links now, because when we close the video, it'll just clear the chat as well.
I guess they can probably follow the YouTube name to find the other videos as well.
Yeah.
But what we'll do is we'll pop those in the description, eh?
Yeah, no, that sounds good.
Cool. All right, well, thank you very much, everyone. Good luck for your exams. Use the weekend wisely. Make sure you do plenty of preparation, going through those past papers, and I'm sure you'll be rewarded in your exam. All right, all the best. Ka kite.